All right, part 3, I believe, of the summation notation stuff. We are going to actually calculate, we're going to add all the numbers from 1 to 100. As you can see, my sigma here got a little bit squashed, but this is, you start at the number 1 as your index, and you go all the way up to 100, just adding whatever number the index is. In other words, 1 plus 2 plus 3 plus 4 plus 5, all the way up to 100, what do you get? This is a very famous thing because there was a very famous school teacher, a very famous story of a school teacher giving this problem to her students. I'm not sure exactly what grade they were in, but they were the teacher needed a little bit of a break to get something else done. Well, so she came up with this to keep the students busy. Just have them add all the numbers from 1 to 100. That'll, give them a good 10, 20 minutes for me to work on something else. And one of the students came back, had an answer within a matter of minutes, possibly even seconds. It was really ridiculous. The teacher was shocked and surprised, and it turned out to be correct. So this famous student is a guy named Gauss, and he figured out a way to simplify this whole problem from an addition problem to a multiplication problem, which sounds kind of silly, right? Aren't multiplication problems harder than addition problems? Well, actually, if you're having to add 1 through 100, you have to do approximately 100 different calculations, and they're all different. There's a chance to make a mistake at every single step of the way. So if you can think about a way to make it into a single multiplication problem, that is just one step, and there may be a few more parts to it, but not really, and there's very, very little chance of making a mistake, and you don't have to go through all 100 calculations. So he's doing it really almost 100 times faster. So let's think about what it is that he did. So let's call this sum. Let's just call it S. Boring mathematicians when they're in their naming. All right. So whatever this sum is, it's some number S. All right. Let's rewrite this whole thing, but let's write it backwards. Okay. So let's write it backwards. Now this is still the same thing. 100 plus 99 plus 98 plus all the way down to 1. All right, and this is also S. Right? We've written exactly the same thing. We've just written in the opposite order. Now, let's add these two things together and notice what happens. This one is 101. 2 plus 99, these are a little crooked, is 101. 3 plus 98 is 101. And so on and so forth until you get to 101. And be careful, because this, we've added the whole sum to itself, so that is in fact 2 times the actual sum that we want. Now, how many of these are there? Well, this is where the nice knowing how many of something is very useful. If we started at 1, this is the first number, this is the second number, this is the third number, all the way up to n, which is the nth number, and that in this case happens to be 100. So there are 100, 101s, which is just English. Let's just ignore that. So it's 100 times 101 is, in fact, 2 times the sum that we want. So we just divide by 2. And there you go. This is equal to 5,050, or 50-50. That's why I started saying 50-50. Okay, so there, I just added all the numbers from 1 to 100. Simple. No, not simple, but very, very, very useful. So let's say you have a sum from I equals 1. Always start at 1 because then the number up here is how many things you have. From 1 to, let's say n. What would that give us? Now, think about what terms you're actually adding together. You're adding the first term and the last term, which happen to be your index terms. And then you're doing it half of the number of times that shows up. So in other words, it's n over 2 times n plus 1, because you're starting at 1 and you're going to n, and there are half of that, half the number of pairs, which makes sense. If you're pairing up the first and last and the second to last, and so on, and they're all giving you the same sum, then there are half as many pairs as there are numbers. Makes perfect sense. And this always comes out to be an integer, not a fraction, because either n is even, in which case the even pairs all pair up, or if n is odd, then n plus 1 is even. So that just works out very nicely. Okay, but this is very, very crucial in dealing with all these sums, because now, for example, if we're going from 1 to 6, let's say we have to do 1 to 6, and we just do 6 times 7, right? 6 times n plus 1, which is 7, over 2, which is 3 times 7, which is 21. Blindingly fast. All right. Much, much faster than adding things all together, especially if there are 100 of them. Okay, now the other ones that we are going to do are kind of just ones that you have to memorize, unfortunately. So I definitely want this to be somewhere. But the other ones are, let's just gonna have to memorize it. So I rewrite it. If we just have I, that's n times n plus 1, all over 2. You can write it that way as well. This is one of the main things. Remember, we also had, if you're going from 1 to n, of just a constant, this is constant times n. Okay, and then sort of within that is the idea, if you bring the constant out front, that the sum from 1 to n of 1 is just n, but that's slightly less important. Then here are the ones to just memorize. If you have from I equals 1 to n of I squared, that is something. And if you have I cubed, this one is surprising. So the non-surprisingly complicated one first. N times n plus 1 times 2n plus 1 over 6. That's a mess, but again, it always works out to be a whole number. So now looking at this, you can kind of see why for something like, if we're going from 3 to 7 of I squared, what we probably want to be doing is doing the actual thing from 1 to 7 and then subtracting off 1 to 2. That's just a side note, but that's one of the reasons why is 1 is the most useful starting index. You really don't want something else, if you can help it. All right, now this one is the surprising one because it's n squared, n plus 1 squared over 4, which is equal to the sum from 1 to n of just I squared, if you notice. That is kind of freaky. So we have, for instance, 1 is, well, 1 cubed. I'm sorry, 1 is just 1 squared. And then 1 plus 2. Whoa. 1 plus 2 squared is the same as 1 plus 8. Let's do it. Yeah, it's this way. 1 squared is 1 cubed. 1 plus 2 squared is the same as 1 plus 8. It's just 9. And then 1 plus 2 plus 3 squared, in other words, 6 squared, which is 36, is 1 plus 8, that is 9, plus 27. This is just really freaky. All right. We are going to stop there for now, but these are the ones that you need to memorize. I hope that I've given you a little bit of an insight into this one, and then this one actually is kind of fun. And this one looks similar, but yeah, it's a doozy.